Let me show some examples. Let's say that we have a basis u1, u2, u3, and that's actually the following vectors: 2, -2, -3, -3, 0, -2, -4, -13, 6. This is an orthonormal basis. Orthogonal basis. And if we have a vector v as 2, -10, 7, we can expand v in the basis B. Note that we have the formula from this section that says that v can be written as the sum of ai, ei. I goes from 1 to 3 in this case, where ai equals to the inner product of v with ei. So this is the case only if the e's are orthonormal. Right now, u1, u2, u3, the list is only orthogonal. We could normalize it simply by dividing each vector with its length. So this is now orthonormal. Perhaps you don't want to do it right now, because what you can see is that actually the norms are not nice integers. So the norm of u1 is square root of 4 plus 4 plus 9, which is square root of 17. u2 norm, square root of the sum of the squares, 9 plus 4, which is square root of 13, and so on. u3 norm, 16 plus square of 13 is 169, plus the square of 6 is 36. So this is square root of 221. Instead of writing it right now, dividing entry by entry, let me just leave the norms there with their notation. So what we know is that the ai is supposed to be the inner product of the v vector with the ei's, and that's right now is the inner product of the v with the u divided by the norm of u, I. And since this is a real number, the norm, we can factor this out. So basically we are postponing using the exact form for the norm until the end. And then we have, for example, for a1, we have the 1 over the norm of u1 times the inner product of 2 minus 10, 7 was the v vector with the u1 vector 2 minus 2 minus 3. So this is 1 over square root of 17, 4 plus 20 minus 21. So that's 3 over square root of 17. And then, and so on, a2, a3. And then when we want to write the v as a scalar combination of u1, u2, and u3, actually what we have is a1, v1, a1, e1, using the orthonormal vectors. But then this is, in this case, 3 over square root of 17. And the e1 is u1 divided by square root of 17, because we normalized it. But actually, if we just want the coefficient of u1, then this will be 3 over 17, and so on. Similarly, we can calculate the other coefficients. So if you want to expand it in terms of the orthogonal vectors, then we don't need a1, we need a scalar multiple of a1, because e1 is a scaled version of u1. Another interesting question is when we have two vectors, 1, 0, 9, minus 9, 2, and 0, 1, minus 1, minus 1. This is in R4. Then find the basis to the subspace of R4, which is perpendicular to both vectors, or orthogonal to both vectors. So orthogonal means that we are looking for a basis for the vectors for the subspace W. So this is supposed to be a set of vectors V such that W is perpendicular to this 1, 0, minus 9, 2, and also W is perpendicular to 0, 1, minus 1, minus 1. So we use now the definition of orthogonality. That means that the inner product is 0. And I'm going to turn this around. So orthogonality is symmetric. If W is perpendicular to this vector, then this vector is perpendicular to W. And then the inner product should be 0. And the way we will write this down is that 1, 0, minus 9, 2, the row vector, because that's a transpose vector, times W should be 0. And also the other one, 0, 1, minus 1, minus 1, multiplied by W should be 0. And then if we collect this together, these two equations, what we get is 1, 0, minus 9, 2, 0, 1, minus 1, minus 1, W equals to 0. So actually we are looking for the null space, basis of a null space of this matrix 1, 0, minus 9, 2, 0, 1, minus 1, minus 1. And we did this before, this exercise, that how to find the basis of a null space. Let's see an example for the Gram-Schmidt process. If we have a set of vectors, minus 2, minus 4, minus 4, 3, 3, 0, minus 4, 4, 7. That would be an extra exercise to see that this is linearly independent. But right now, and it will come out anyway from the Gram-Schmidt process, using the Gram-Schmidt process, we will get the orthonormal basis in R3. Yeah, so the process is that if we denote this with V1, V2, and V3, then E1 is simply the V1 vector normalized with its length, which is square root of 4 plus 16 plus 16, multiplying the vector minus 2, minus 4, minus 4. So this is 36, which is 1 over 6 actually, so that's not a very bad vector, but it's still not an integer vector, so we're gonna get 1 over 3 minus 2 over 3 minus 2 over 3 as E1. So after we have E1, E2 is V2 vector minus V2 inner product with E1, E1. So this is 3, 3, 0 minus 3, 3, 0 inner product with minus 1/3. Actually, let me factor out 1/3, because then I can I don't have to work with so many fractions. And then I also have the 1/3 factored out when I use E1 here. It's 3, 3, 0. I'm gonna factor out these two 1/3 scalar multipliers as 1 over 9. And then the inner product, 3 minus 1 minus 3, 3 minus 2 minus 6, 0 minus 2, 0, times minus 1 minus 2 minus 2. So here this is minus 9, and then that means that it cancels with 9, and we get actually plus and then minus. So this is 3 minus 1, 2, 3 minus 2, 1, 0, minus 2, minus 2. This is the E2 vector. That's actually E2 star vector before normalization. And then we normalize it, A2, to be E2 star divided by its length. And the length is square root of 4 plus 1 plus 4, which is 9, times E2 star. So this is 1 over 3, 2, 1, minus 2. For E3, we need more work. And again, first we obtain the unnormalized vector as V3 minus V3 E1, E1 minus V3 E2 inner product times E2. V3 was minus 447, and then we need the inner product of this with E1, so 1/3 minus 1 minus 2 minus 2, so that I don't have to work with so many fractions. So this part here is V3 inner product with E1 times E1, and then we also have to subtract the V3 inner product with E2, which is again 1/3 times 2, 1 minus 2, and then the 1/3 the vector 2, 1 minus 2. Collect, again I collect the 1/3, so this is minus 1 over 9. Then the inner product is minus 4 times minus 1, 4. 4 times minus 2, minus 8. 7 times minus 2 is minus 14. And the vector minus 1, minus 2, minus 2. Here this is minus 18. So altogether this will be plus 2. And then minus, collect the 1/3, that's 1 over 9. And then the inner product of this vector with that vector, so this is minus 8 plus 4 minus 14. And the vector 2, 1, minus 2. So this is 2 plus 2. This is minus 2, minus 4, minus 4. And this is again minus 18. So again, this will be plus 2. So this will be 4, 2, minus 4. So altogether, this is minus 2, 2, minus 1. This is the unscaled version of E3, denoted by E3 star. And then to get E3, we get the E3 star divided by the norm of E3 star, which is 1 over 3 times the E3 star vector minus 2, 2, minus 1. So this is actually relatively nice because we only have fractions and small fractions like 1/3. In other problems it can be much more uglier with square roots. This Gram-Schmidt orthonormalization can be also applied to function spaces. For example, we could have a function f of x equals 5, g of x equals 2x plus 8, and h of x equals minus 7x squared. So from the degrees of these polynomials, we can see that these are actually linearly independent. If we look at, for example, the continuous functions on the interval 0, 4 with inner product pq, which is the integral from 0 to 4 px qx dx, then from this fgh list we can create an orthonormal list. Let me denote it with E1, E2, E3, although these will be functions. Yeah, the orthogonalization process is the same. We have E1, which is f divided by the norm of f. This is 5 divided by, and the norm of 5 is the square root of f inner product f, which is the square root of the integral from 0 to 4, 5 times 5 dx. So this is 25 integrated over 0 to 4. That's actually 100. The square root of that is 10. And this is 1 over 2. So E2 is a start version, unscaled version. Unnormalized version is g, the second vector in the function space, minus the inner product of g with E1 times E1. So this will be 2x plus 8 minus the inner product is the integral from 0 to 4, 2x plus 8 times E1, which was 1/2, and then times 1/2. So this will be 2x plus 8 minus, we can factor out 1/2, or we can write this in front, and then simplify by 2 to get integral from 0 to 4x plus 4 dx. The integral of x plus 4 is x squared over 2 plus 4x from 0 to 4, 2x plus 8 minus 1/2, 16 over 2 is 8 plus 16, and then at 0 it's 0. So this is 2x, 24, 12, minus 12, so 2x minus 4. This is the unscaled version. And then to get the normalized version, we have to divide this with its norm. And the norm is the square root of the integral from 0 to 4 e2 star square, which is the square root integral from 0 to 4, 2x minus 4 squared. So this is 4x squared minus 16x plus 16 dx. It's not difficult, it's just tedious. We get 4x cubed over 3 minus 8x squared plus 16x evaluated at 0 and 4. The nice thing is that at 0, at the lower limit, mostly everything will be 0. And at the upper limit, this is 256 over 3 minus 16 times 8, 128, which is 8 over square root of 3. So that means that E2 is E2 star, which was 2x minus 4, divided by 8 over square root of 3, which is 2 square root of 3 over 8x, and we could simplify by 2, minus 4 square root of 3 over 8. Again, we could simplify by 4. And then E3, it's even more calculation, but there are no tricks about this.